Hey y'all, welcome back for another episode of Science and Engineering in KSP. I'm your host, Andy Leonard. This week we are going to apply what we've learned in episodes 1 and 2 to orbits. And we're going to learn about geostationary orbits, we're going to talk about Molniya orbits, and we're going to talk about polar orbits. But there's a little bonus here because we're not going to be looking at polar orbits in KSP. We're going to be using a different piece of software that if you're into space, you'll probably really like, and I'm really excited to share it with you. This episode's going to be a little different. I'm just going to hop straight into KSP and start doing things there. So no PowerPoint to keep me focused while I do a quote lecture unquote. So forgive me if I stumble about while doing things in KSP. All right, let's begin. So here we are in orbit around Kerbal. Bob is our pilot today. We are in a pretty circular, pretty equatorial orbit. Both of the relevant orbital elements are 0 to 2 decimal places. And Bob is moving at a pretty good clip around the planet with an orbital period of about 33 minutes and moving at about 2.25 kilometers per second. So he's going to circle the planet several times in one day. Say we wanted to turn Bob here into a communication satellite or a GPS satellite or any other satellite where it's important to have a fixed view on one patch of the Earth. You probably know where I'm going with this, but we need to raise his orbit far enough that his orbital period matched the length of a day. So how do we do that? Well, if you remember back to the first video, we talked about Keplers Laws, and Kepler's third law is relevant here. If you remember, the equation for the period is 2 pi times the square root of a cubed over mu. So we rearrange that to get the radius we need to be at. We get the semi-major axis is equal to the period divided by 2 pi all squared times mu, and we take the cube root of all of that. But before we go plugging in numbers here, we need to stop and talk about time. And not the nature of time. Nothing we can really do in game is going to change the way that time behaves. But we need to talk about how we measure time. And we need to talk about the concept of solar time versus sidereal time. So what is the difference between solar and sidereal time? Well, look at this screenshot that I took. The yellow represents solar time, and the red line represents sidereal time. And I've taken 4 days here, day 1, day 2, day 3, day 4, obviously greatly exaggerated, but it'll prove our point here. Now, on the first day, they're coincident, but on the second day, you see that our solar time is represented here, and then the further along in our year we get, the more and more slanted this line is, and the further away it is from the line representing sidereal time. That's because a solar day is defined as the time it takes for the one point on Earth to turn 360 degrees and be pointing back at the sun, starting from being pointed at the sun. And sidereal time is defined by a fixed direction. Now, what do you think that is? If you guessed that the fixed direction was the fixed point of Aries we talked about in the video last week, you are 100% correct. And so the reason we need to worry about the sidereal time going into a geostationary orbit is because we need to be fixed with respect to the Earth alone, pretty much. Basically, just consider the Earth our reference frame and not worry about the Earth in reference to a nearby sun or anything like that. So that's why it's important. And for the first demonstration, we'll worry about it. It doesn't come up so much in KSP, so we're not going to worry about it for the next couple of demonstrations. Just thought you should be aware of it. But anyway, so hopefully that little detour gave you an idea of what we need to do. So we need to be very careful to consider the sidereal day of Kerbal rather than the solar day. And if you look on the KSP wiki, we get the sidereal day on Kerbal lasts 21,549.425 seconds. Now, when we plug that into our equation for the semi-major axis, we find that we need to be out at 3,543.684 kilometers. And when we subtract the 600 kilometers of Kerbal's radius out from that, we figure out we need to have an apoapse altitude of 2,853 kilometers thereabouts. So at some point we are going to go more in depth into maneuvers and how to get where you want to go. For now, all we really need to know in order to change our orbit is that when we want to raise our apoapse and get it going out here, we just need to fire prograde. So we're going to light our engine and we're going to wait until we have an apoapse of 3,453 kilometers. So by this point we have finished our first burn. Our apoapse is 2,853.6 kilometers. So we're going to go out here and we're going to set another maneuver. And we are going to circularize our orbit by performing a Hohmann transfer. Not a Frohman transfer. We're not talking about the Sausage King of Chicago. A Hohmann transfer. And in another episode, we'll get into why a bielliptical Hohmann transfer is more efficient than a Hohmann transfer if you have the time to spare. But for now, in the interest of keeping maneuvers simple, let's just say we're going to fire prograde and we're going to try and get into a geostationary orbit. So by this point, we have completed our circularization burn, and the results were pretty good. Our apoapse and periapse height only differ by 2 kilometers. So we are in a circular geostationary orbit. And our inclination is up a little bit, but it's still going to be, low enough to not matter. So let's switch over to the vessel, make sure we're in chase cam here to get the best effect. And let's just keep the camera kind of fixed and see what happens when we speed up time. Yeah, you see we are moving because we can see the stars in the sky move, and we can see the shadow on the planet change as it experiences night and day, but we're covering the same area, the same geographical area of the planet, and we will continue to do so for a very long time. Now, these very small variations will eventually kick us out, but I think we'd have to propagate the orbit over a period of thousands of years to get a very big difference. So all the nice folks at home are getting their TV and their GPS signals, and we did it. What if we wanted to make sure that we had a satellite over a specific region of Kerbal? Like, say, for example, I'm trying to find it. I think this would be the KSC here where we launch from. Let's say we wanted to make sure that we were hovering directly over KSC forever. How do we make that happen? And so we're back in our 100-kilometer circular orbit over the equator, this time with Valentina. I've gone ahead and I've marked Kerbal Space Center with a flag here because it's going to be a lot easier to get to a geostationary orbit directly above it if we can keep track of where it is. So how do we do that? Well, let's take a second and think about what we know. We know that we need to get to an orbit with an apoapse altitude of 2,853 kilometers. We know that we are at 100 kilometers, and we know that Kerbal rotates at a rate of about 360 degrees per 21,600 seconds. So that's 6 hours in seconds. How can we use that information? what we need to do is we need to figure out, since we're moving and Kerbin's moving below us, we need to figure out how to time our apoapse burn, like our burn to make an apoapse basically, so that Kerbin rotates underneath us and positions KSC directly under it. So how do we go about doing that? How do we know how long it's going to take to fly from, say I start burning here. How do we know how long it's going to take to fly from here to here? Well, if you think about it, that's just basically half an orbit, right? So if we burn, we make this our periapse, this is our new apoapse, and that's just half an orbit. And we know how to get the period of an orbit. So all we have to do in this case is divide the period we get from that equation, by 2. And so what's our semi-major axis of that orbit going to be? Well, we have an equation for that too. All we have to do is take our periapse radius plus our apoapse radius, our intended apoapse radius, and divide that by 2. And so when we do that, we get a semi-major axis of 2,376.842 kilometers. Plugging that in to the period equation and dividing it by 2, we get a period of 6,125.5 seconds. Basically an hour, 42 minutes, 5 seconds. So what are we going to do with that information? We need to figure out the angle that is swept out by Kerbal Space Center over that period of 1 hour, 42 minutes, and 5 seconds. We need to figure out basically where will it be. And it turns out we take 360 degrees, divide by 21,600 seconds, and multiply that by 6,125 seconds, and we get an angle of 102.09 degrees. So that means that KSC is going to move about that much. Look where I'm pointing. It's gonna be here in an hour and 42 minutes. So what we need to do is we need to take that point where KSC is gonna be, and we need to burn 180 degrees opposite it, so that we raise our apoapse here, and KSC will be there by the time we get to apoapse. So in order to do that, one of the benefits of having these flag markers here is that it gives you coordinates, latitude and longitude coordinates, and we're at 74 degrees west. So what we need to do is we need to take 180 minus 102.9, and then we get 77.91 degrees. And then what we do is we take 74 degrees west, subtract the 77.9, and it turns out that we have to burn at a longitude of 176.1 degrees east. And here we are now. We've finished all of our burns that we need to do, and I think I burned just a little bit too late, because as you can see, I'm not directly overhead, but I am pretty close. That's not too big of an angle. We're not going to lose too much data going that way. But what if there were an angle? What if you didn't live on the equator, or somewhere within decent view of the equator? What if you lived up in a northern latitude or a southern latitude, and the satellites couldn't see you that well if they were in a geosynchronous or geostationary orbit? It turns out that if you're living here and the satellite's trying to broadcast information here, you're going to lose a lot of data unless you have a very prohibitively powerful signal. So geostationary orbits like this don't really work for those northern latitudes. So what did they do? There's a really cool piece of Soviet wizardry called the Molniya Orbit. And I guess we'll switch over and start talking about that. So here we are in the Molniya Orbit, or almost the Molniya Orbit. And I say that because one of our orbital elements doesn't match the real life orbital element. Our inclination's good. Our inclination is 63 degrees. That is the value that the Molniya orbit takes. And we need that because, as we were talking about, we need to get to those high latitudes. And as we talked about last week, your inclination is basically your latitude limit. Our argument of periaps is good, 270 degrees. So that means that I think our equator would be about here-ish. So from there, in the plane of the orbit, we go 270 degrees. So our periaps is at the lowest possible point over the planet. So our apoaps is over the highest possible point over the planet. So that's good. Our period is half a day, which is the length of a Molniya orbit, which is the period of a Molniya orbit, I should say. The only thing that isn't kind of stacking up to real life here is the eccentricity. Now, satellites in Molniya orbit about Earth have an eccentricity usually between 0.73 to 0.75, somewhere around there. But the highest we can get and retain while retaining this period is 0.69. If we try to recreate the orbital eccentricity of 0.736 that I was initially going for, we get a periaps distance of 576 kilometers, which when you subtract out the radius of Kerbal, you get an altitude of negative 24 kilometers, so you're inside the surface of the planet. So that wouldn't do. But I mean, for all intents and purposes, this is basically a Molniya orbit, even if the eccentricity doesn't match what it would in real life. So let's switch over to the spacecraft and let's get a view of what's going on. See, and as we move away from the planet, we're slowing down and we're spending more and more time over this altitude. So we're broadcasting to these latitudes here, right? And they're getting all this information, and we can see them, and we're starting to go back down again, and we're just going to zoom past periaps because, you know, we're people from super high latitudes, and we don't really care about what's going on down there. We need coverage for us. So we come back up, and we're covering the opposite side of the planet because, remember, our period is half a day. So we come back up, and it's us. We're getting it again. So in real life, you can, with a constellation of 3 satellites in a Molniya orbit, you can ensure full coverage of your ground site. So this is NASA's Eyes on the Solar System. If you want it, you can just Google NASA's Eyes, and you'll be able to find it. It was developed by JPL, the Jet Propulsion Laboratory, with the cooperation of their backing institution, the California Institute of Technology. And what's really cool about it is that you get a real-time view of the solar system, and it's just awesome. You see all the planets, you see all the different missions. You have OSIRIS-REx on its way to Bennu here. You have the Kepler Space Telescope, and if we scroll out, well, we probably won't be able to see it from this far out, but yeah, here's New Horizons coming out past Pluto. Here's Voyager 2 making its way out of the solar system. Just a really, really neat piece of software. And so we're going to talk about polar orbits specifically. I'm not just going to geek out over this program, which you should go get. Yeah, we're going to talk about polar orbits specifically with the help of the GRACE mission. If we scroll in, you can see there's a GRACE 1 and a GRACE 2. And this is a really neat mission, and it kind of makes me proud to go to UT, because UT did a lot of work on this mission, and I'm very, very lucky to have taken classes from people who worked on this mission. So what are we looking at here? Here's Grace 1, and it looks like it's following this satellite here, Grace 2. And if it looks like it's following it, that's because it is. They're about 220 kilometers apart. And this little wavy line in between them represents a sub-millimeter accurate microwave ranger between them. So it's getting the distance in between them. Now, why would we want the distance in between them? They're about 220 kilometers apart. Well, as it turns out, the Earth doesn't have uniform gravity distribution like our planets in KSP do. Well, I mean, the planets in KSP are basically point masses, right? Not so in real life. So with this different distribution of mass, since one satellite is about 220 kilometers ahead, it's going to start going around and above certain geographical features first. And that mass is going to grab Grace 2 and accelerate it just the tiniest of bits. And so the change in distance between Grace 1 and Grace 2, if you get that data, you can figure out the mass distribution where Grace 1 is. Now, this is really, really helpful. GRACE stands for the Gravity Recovery and Climate Experiment. And so studying the distribution of mass on Earth is really, really helpful in understanding climate change. As the ice shelves melt and everything, we can monitor how much ice mass we're losing and what mass is being converted into water. And we can also monitor ocean currents, water cycles on land, and other cool stuff like that. So it's just a really, really cool mission. And obviously it's in a polar orbit because we want to monitor the ice caps, but we also want to see what's going on all around the world. And as we talked about last week, if you're in a polar orbit, that's the only way to guarantee that you will fly directly over every part of the world at some point. I think I'm going to end the episode here. Well, I'm not going to end quite yet. I have one more treat for you. So if we look at Mars, another really cool thing about eyes is that you can go back and forward in time, right? So you could go forward in time and you could see where Osiris-Rex rendezvous with Bennu, but we could also go back in time to August 6th, 2012. And here is the Mars Science Laboratory. This is the spacecraft that delivered Curiosity to Mars, and it makes sense that since this app was developed by JPL, and they were the rock stars on this mission, they'd want to animate it and highlight it and take you on a tour of it. So let's check it out. Yeah, we're just getting ready to pop off the cruise stage here. And blammo, it pops off, and you can see we're reorienting the lander. And I think I'm going to speed this up to so we're going like 1 minute per second. So it'd only be 7 seconds of terror versus 7 minutes, right? And you can see the atmospheric effects, not quite KSP level, but they are represented. And we're making our descent. And we made it through the atmosphere, which is pretty cool. Now, notice that all of Mars isn't represented in such high fidelity as the landing site here. Like I said, they paid extra attention to Curiosity. And see, they dropped off ballast, and there's the parachute being deployed, giant parachute for the thin Martian atmosphere. drop off the heat shield, and Sky Crane's away with Curiosity below it, and you can see it vectoring here. Man, the camera controls take some getting used to. And yeah, we're just coming down really slow, trying to keep our attitude, and hovering over, hovering over, hovering over. Yep, seems like a good spot. We're going to lower her down. And bam, touchdown. And then we cut the linkage in between, and the descent stage goes bye-bye. And yeah, that's how Curiosity came to Mars. And I thought it was really cool of JPL to have this software for free for the public. Thanks for watching this episode. I had fun making it. Hope you had fun watching it. And I will see you next week.